Thank you, Rogelio, and thank you everybody for being here again. So, okay, last time I was like introducing rigid geometry from as a parallelism between non-Archimedean geometry and scheme theory. And I told you that we pretty much do the same. I mean, you start defining some appropriate objects, which are called affinoid algebras. Um, so these are just algebras over CP. CP is the completion of the algebraic closure of the p-adics. For technical reasons, you need to consider that. And you consider categorical epimorphisms from a special algebra, which is called the Tate algebra, which is supposed to represent the algebra of analytic functions over the unit disk. And then you call them affinoid algebras for historical reasons. This is exactly like the same approach that you take in scheme theory, since to define affine varieties or varieties in general, you consider some epimorphisms from polynomial algebras to algebras defined over QP. So I told you that then you pretty much follow the same path in the sense that try to induce a topology on these affinoid spaces or affine spaces by looking at a special family of distinguished open subsets. In the affine case, in the scheme case, what you consider are complements of hypersurfaces inside these affine spaces. And in the analytic case or in the rigid case, you consider what are called rational domains. So the distinguished feature of these guys is that you can perceive or you can sense that these subsets, special or open basic subsets, are spectra of rings, right? Again, why? Because since you are taking the zero locus of some regular function, you have the, let's say, the right to invert this function over this open set, and then the algebra that you get by inverting this element is precisely the algebra of regular functions over this set. And the same works for rigid geometry. You consider two elements in your affinoid algebra. These guys induce functions over the spectrum of A just by valuing, taking the absolute value of the image in the residue field, which is again K or Q or CP, because CP is algebraically closed in this sense. And what is good is that, again, this special set, which is the points where are bounded, such that are the value of F at these points is bounded by the value of G at this point and by above. These guys, once again, the maximal spectrum associated with some affinoid algebra. Okay, we were here last time, and I told you that this approach is not correct because there are two reasons. So continuing with our comparison, the family of basic subsets in schemes, the whole space is quasi-compact. And the second reason is that the segment df sending to R f minus 1, this is a sheaf. Well, this extends to a sheaf. and both of these properties fail in the rigid case. So U F G for F and G in A. With this topology, with topology induced by these guys, X equals max A is not quasi-compact. And the second thing that fails is that the assignment UFG sending to A X X G minus F or something like that, perhaps changing here the roles of the F and G. This does not extend to a sheaf. And basically, this is everything that fails that prevents us from following the same path from scheme theory to rigid geometry. So what do? Well, we force this topology solution, this force this setting to be what we want. Namely, we don't consider all the coverings by open sets by affinoid sets, right? I mean, if I were to define topology using these rational sets, if I were to define the topology using these rational sets as my base, then the fact that it is not quasi-compact prevents me from getting something useful. So what I do is just to filter the covers which give me quasi-compact behavior. And then what happens is that once that I filter the covers for just to consider them those which give me quasi-compact covers, then automatically this assignment becomes a sheaf over the corresponding Grothendieck topology that I define. So just let me put this in written form. Once we consider only finite coverings by affinoid sets, once we consider only finite unions of rational affinoid domains, together with affine covers of them by rational subsets, we get rigid geometry. However, the price to pay is to abandon the set topology realm and to embrace Grothendieck topologies. So if you are happy with this, then you may stay at a rigid level. I mean, you may start doing geometry in the rigid sense, because now this assignment sending finite unions of rational to this kind of algebras, right? This gives you a shift. So what you end up with is with your affinoid block, which is some Grothendieck topology defined on the category of rational of finite unions of rational domains with finite covers of them, and then you get a shift over there. And this is what is called X-free, where X is max of A. And what is wonderful about this is that you can glue this type of spaces, and at the end of the day, you can construct spaces which are not affine. So let me just put a concrete example before changing a little bit the subject. For example, something which is not particularly geometric about this construction is that rigid spaces come equipped with some sort of carcass, some sort of, how to say, some sort of skeleton. And you cannot get rid of the skeleton, in the sense that the affinoid structure is defined by some covering, some specified covering that you cannot get rid of. So for example, just let me finish with, let me consider the projective line, and let me do several pictures, because I will need this later. So for example, here remember that K is algebraically closed and of characteristic 0. Okay, so from in algebraic geometry, this guy is just defined space together with the point at infinity and some genetic point. If I am working in analytic geometry, I have two cases, like I have the Archimedean and I have the non-Archimedean. And the Archimedean is just choosing K equals C together with usual topology. So what you see is the usual Riemann sphere. With the usual topology. So you can take small subsets, small balls around any point, small as you want. And this guy is Hausdorff, and it is nice. However, what can we get with when the K is not the complex numbers or the real field, which you get? That could be a nice question. What do you get if K equals R, right? Which is the other Banach field that we have at our disposal. So what you get is the real part together with a copy of the upper hemisphere. What about the p-adics, for example? K is equal to p-adics and the p-adic norm. Well, in this sense, you cannot do this anymore. And what you end up with is with some sense of infinite filtration. Like you start taking the ball with its radius 1, then by considering an homotopy of this, you can consider the ball with radius 2, and then you can iterate this, consider the ball with radius 3, etc. The ball with radius n and big. And then at the end of the day, if you take the union of all these charts, you end up with the affine space together with the extra point, which is the 1-point compactification of this guy. And this is the rigid structure of your analytification of T1. You cannot get rid of this filtration. You have a similar filtration over the complex numbers, of course. For example, you start with the unit disk, then you start with the disk of radius 2, then the radius 3, radius n, etc. But this filtration is not relevant over the complex numbers, since you can move freely away from the origin and do whatever you want. However, over the p-adics, but the topology tells you that everything has to be or can be centered around the origin, and you cannot get rid of this. And all these balls appear as affinoid spaces. So in the example, if you take a look at the notes, you can see precisely, in a precise way, how each ball of any radius can appear as an affinoid space just by changing just by doing a homotopy at the level of the variable that you are considering as your describing variable of your disk. Then it is difficult to, in my opinion, when one introduces rigid spaces as these kind of guys, it is not very natural from a geometric point of view. But this, since this is a site, so X3, well, some features is that if you have X equal, let me say, max A rig. By this, I mean this is the category associated to the affinoid spaces or rigid or rational domains of A, the topology, the Grothendieck topology that I just discussed, and the sheaf over this guy that assigns to an affinoid domain the algebra that you get by pasting together the algebras that give it as a union of affinoids or as rationals. Then, and if you have another guy, max B, and this is CB, D, O, maybe. Then, and if these guys agree over an open set, then you can consider the union of these two spaces along U. And this is once again a rigid space. So, for example, you can define the rigidification of P1K as gluing together the analytification or the rigidification of A1 together with one more, identified along the rigidification of the torus, right? As you do in scheme theory. So from this point of view, rigid spaces are nice. These are sites, right? As in Felipe's talk. So this guy is a topological, well, is a category with a topology equipped with a sheaf over that site. And then you can do geometry in the form of sheaf cohomology. So you can define sheaves as in Felipe's talks, sheaves over a site, and then you can do geometry by computing cohomology groups and specifying some geometric behavior using them, right? And so this gives some sort of geometric flavor to theories or to some analytic theory, where the topology is not right or is not as good as we used to consider. So just let me tell you that some people is more geometric, right? Some people tend to be more geometric, and they want a true space, topological space, not just a site. And so, since let me remind you that John Tate introduced these ideas around 1961, and then the German school Grauer, Bremer, etc. They took the ideas of Tate and developed what is called affinoid geometry. So if you want to understand precisely which are the algebras that I am considering here, concretely, what is this guy? For example, what is a double brackets, angular brackets together with a new variable divided by some ideal? You need to do some Banach algebras theory. And I'm telling you that this theory is very well developed by the German school, and you can find more maybe in the bibliography of the notes. You can ask me about references. So let me start. Let me see if I get anything. So this is the rigid structure of P1 of A1. Sorry. Let me see if I have. Yes. So the next step, I'm in equation 13. I am giving you the concrete rigid structure of the affine line. To just take what is very important here, and sometimes we forget, is that it is absolutely necessary for rigid geometry to find one guy such that the absolute value is not trivial. So you need some guy whose absolute value is inside the open unit. And all the constructions in rigid geometry depends on finding this guy. So this is why rigid geometry does not work with trivial valuation. Right? Because with the trivial valuation, we don't have this kind of guys. So this restriction can be forgotten if we switch to Berkovich approach. So anyways, just to remind you that the last section probably that I'm going to explain here is about Berkovich spaces, right? So the motivation behind Berkovich spaces is that we wanted a true topological space. And then Vladimir Berkovich, around 1989, 1991, perhaps, he was studying to which extent this was possible. I mean, can we do p-adic analytic geometry with a true topological space, right? And the answer is somewhat yes, but not quite. I mean, the setting is not, it has its particularities. It is a really beautiful subject, but along the years, we have learned that this is not what we want. This is not the definitive answer about this question. So anyways, this was the motivation behind, or some of the motivation behind Berkovich development, and we are now going to introduce this, right? Okay. So again, it is possible to define the category. It's possible to define a category of Berkovich analytic spaces over a non-Archimedean valued field. Of course, I am considering here that the evaluation is not trivial. But in Berkovich setting, this is possible also to define analytic spaces with trivial evaluation. And in general, introducing this kind of theory is really complicated because you need to take into account several subtleties of Banach algebras, which are not present in Tate's formalism. For that reason, I'm going to focus here just to define how to analytify a variety. The particular benefit of this approach is that you just need to consider one particular category of Berkovich analytic spaces, which are called good. And good analytic spaces are locally modeled on some generalization of the finite spaces produced in Tate's approach. And they are more convenient to work with because it is not as difficult as the general theory, and it still serves one meaningful purpose, which is to consider analytic spaces associated to algebraic varieties. Right? So what is good, and why do we care about this? So good is an adjective, but it is also a definition. It is not just something which is not concrete. I am not going to define Berkovich analytic space in general, but you have to assume that the category exists. That means if you give yourself a field with an absolute value, then you can construct pretty much in the same vein as a complex case, category of analytic spaces. These are guys which are topological spaces together with a sheaf of analytic functions. And inside this big category, there is a special place in which good spaces sit. And the quality of being good is if every point of your space has an affinity. So this is not true in general, which is kind of how can I say it? It's kind of why this is the reason why the theory is really hard, because this non-homogeneity hypothesis or result. So just let me tell you what happened. So we know, let me just remind our purpose. We have here C bar. We have here an analytification functor, which goes to C infinity AN, right? Here C infinity is just C equipped with absolute value, which is useful. Then what we did is to take CP, well, this is rather, let me call it QP bar, and I define the functor to Q for CP, right? And but this was not an, this was free, right? And CP is a QP together with the absolute value. So here was x, it went to xn, and here it was x and went to x3, right? So what I'm going to do now, well, I am telling you that you have to accept that there is a category which is called CPN. Maybe for Berkovich. That sends a variety to xn, right? And the difference between the red and the black is that these are topological spaces, and these are sites, authentic sites. But basically, the necessary concepts to do this transition have been already introduced. Okay, so let me start. So my purpose or my goal is to be able to analytify variety. So as I said, the main feature of varieties is that locally they are closed sets of affine spaces. You can define patches like this. So I am going to tell you how to do this for an affine variety, and then since the spaces are good, you may glue them back together to create non-affine spaces. I need to tell you that this is not possible in general for general Berkovich spaces. It is really, really hard to glue them back if they are not good. Okay, just let me put that here. This is a warning. So rigid spaces can be glued, but Berkovich spaces, which are not good, um, can be glued also, but it is difficult to do it. So this is why I'm not going to introduce analytic spaces in general. Okay, so let me consider an affine variety, which is the spectrum of a finitely presented K algebra. So the analytification as a set is just some set of seminorms, and I am going to endow this set with a topology. The topology is some weak topology induced by some evaluations. This is the meaning of definition 8.2. And this resulting space is going to be Hausdorff. And this gives us a meaning or a certain familiarity with what we have already done with complex case, right? This is what we get in the complex case when we analytify. We get a refined topology, which is Hausdorff. Okay, so just let me tell you what. Imagine that X is a spec R. R is K x1 up to xn divided by some f1 fs. So what is xn? To consider all the functions which go from R to the reals, such that W is a generalized valuation. Or perhaps I should say just absolute value. In the sense that you need this guy to be subadditive You need this guy to be multiplicative. You need this guy to be non-trivial. It has to send 0 to 0, and that's all. Also, there is an important feature because K sits inside here. I am thinking about CP. This guy has his valuation. Sorry. This is the p-adic absolute value, which is defined on CP. Since this guy is K-algebra, you have this structure morphism, and these W are supposed to commute with this setting. So there you go. This is the set that you assign to this particular affine chart. And the topology is hard to describe since classically, if you go to an old book about the Berkovich spaces, it is telling you that any map or any guy here defines a map, an evaluation map like this, which you take your favorite semi-norm and you take the value of f, which is a point here or an element here. You take the value under W, which lands in R positive union 0, right? So this is a family of functions for f in R, right? And then they induce to take the smallest or the weakest topology such that all these guys are continuous. And this gives you a topological space. And the result is that the resulting topological space, these guys have. And we are going to see some other qualities of it after the break. But there is another way of introducing the topology, which is more natural, and this is called the cylinders. So for any W in R, to take and for any open subset here, recall that this guy is a topological space because it sits in R with the usual topology. What you do is to take all the subsets of the form. I'm sorry, here is F in R. So I am going to finish here before the break to define the cylinder defined by U, F, and U as all the semi-norms which land in U. And you can show that the family of all these sets for F in R and U, an open subset of open. This is the same as the Berkovich topology that I defined, but this has the advantage of being more geometric rather than just say, okay, you swap in under the rock the difficulties by specifying this the weak topology. You can have a sense of what an open looks like. So this is the only thing is that this is a subbase for the Berkovich topology. Okay. So I guess I have to make a pause.
Yes.
I don't know if I'm correct.
Yes, that's right. That's right. So we go to a pause for 10 minutes and then we return, okay?
Okay, great. So this is how you assign a topological space to this affine piece, right? So I told you that the cylinders which is U, F, let me call B just to make a distinction here. F is an element of R and B is an open set. Here, this guy is considered with the topology induced by the embedding into the Euclidean space. This form subbase for the Berkovich topology. Okay, so you have a topological space, and it is possible to assign to this topological space a sheaf of analytic functions, pretty much in the same way that we did for Tate geometry. Namely, you define here rational domains. In the exact same way as we did for Tate. And you can assign to these rational domains. You can, it is not completely true that here the assignment of UFG, recall that this was like all the points. Here you can think about max A if you are working with rigid, or you can think about XN if you are thinking about Berkovich, such that the value of X with respect to the norm was less or equal than the value of X with respect to the norm. So recall that these were like the rational sets, and then we consider a finite covers of finite unions of these guys, and we try to assign to them a sheaf of regular or analytic functions over the union. So in this way, Berkovich topology does not solve the topological problem that we had with Tate. And this is something which is kind of difficult to get, because we thought that this was going to solve that problem, right? So Berkovich, if you take a finite union of these guys, and then somehow you fabricate an affinoid algebra out of the singular affine algebras, or of the single affine algebras that you are fabricating with this construction. This gives you a big A. You can glue these algebras back. This is not a sheaf in this case either. But you can try to approximate sets by open sets, and this is what gives you the true sheaf, right? So for example, the true sheaf is obtained by approximating by by open sets. So the sheaf is the following. You take an open set here, and then the value of the analytic functions here is just to take the affinoid algebra associated to affinoid domains, which you can think about finite unions of rational sets inside this space of valuations. And then you take the limit over all these guys where B is contained. So this gives you a true sheaf over a true topological space, and this is what we call the Berkovich space associated to the affine piece. Okay. So now what I told you is that whenever you have good Berkovich spaces, let me just put this here just to recall you that these are good. Okay. Then you can glue these affine pieces back and recover a global space out of local ones. So if X is an algebraic variety over QP, then you take an affine cover and define Xn to be the union or the gluing of UEn. And here UEn is just the space that we assigned to R, right? It's just a space of valuations which are somehow linked to the original one by asking this diagram to compute. So the basic example is once again, sorry. The basic example, let me recover from my previous table, is P1. And let me tell you what's happening here. Okay, so if you do analytic geometry, but not in the Tate case, but in the Berkovich case, what you do is recovering the generic point. You put it back, and then you start filling out this discrete or this blue or this chassis with valuations, and the valuations are somehow what gives you the topology of this Berkovich space. So valuations can be deformed over the reals, and this basically gives you the famous tree-shaped form that you see in other kind of text, right? So the form is that the difference between the blue drawing and the green drawing is that you get more points from Berkovich approach than from Tate's one. From Tate's approach, you forget the red point, which is the generic point. And you only take into consideration the closed points, which are the blue points. With Berkovich, you get to put back the generic point and start deforming some norms defined over the residue field of this point, and this gives you the topology on this namespace. And what I'm telling you is that the same construction that we consider for rigid spaces, in which we glue back we glue back two copies of a fine line together along a torus to construct the projective line. This is also true for Berkovich. So P1 Kn is just AK1N union A1N K along the analytification of the torus. So this is one good feature that we get from good spaces, right? That we can glue back, and also there is this concrete description of the sheaf, something which we didn't have in Tate's notion. But it is not what we wanted. I mean, we wanted to consider true rational sets, and we wanted to consider the natural shift that arise from them. Just to consider a rational and then assign it directly the affinoid algebra that you get from casting them together. And this is not true for topological reasons. So this is why sometimes Berkovich theory is limited when we try to recover a version of complex analytic geometry in the non-Archimedean case. But it is really nice because you get a topological space together with a sheaf, and this gives you some meaning of geometry, right? So let me tell you how can you see these spaces as fiber spaces. This is something that I really like because it gives you some a concrete picture of what's happening, and also what happens with the Tate rigid spaces in this context, right? So this is like the fibration over the spec. No, it is not true of vibration, but it helps. The word it helps. Okay, so again, let me consider an affine scheme. So let me consider the analytification, right? So the analytification sits here. And then if I consider a point here, you can work this out. The kernel of W is prime ideal. The kernel is just the elements which are sent by W to 0. So if you take a guy here, you may assign kernel here. It's a prime ideal, and this map is continuous. Recall that this is not just a set. This has a Berkovich topology, and this has a Zariski topology. And then you may wonder what is the fiber. The fiber is just the set of all the valuations over some residue field which commute with the inclusion of k inside the residue field of k of x. So just to be clear, if you take a point in your scheme, then the residue field is an extension of your base field. So you may consider this instead. So you have your valuation which goes here, and I'm telling you that this space is precisely all the valuations, I mean all the absolute values which go from this space to this set, from this field to this set, such that this could, okay? But here W is a true absolute value. This means that it has no kernel. So you may feel this diagram like this. And you get a parametrization of your analytification as pairs. So let me put this as a point instead of as a prime ideal. This is a point here. And this is telling you, so here is a valuation, which goes from the residue field to R non-negative. And this is telling you that the corresponding point in the analytification consists of a point in the spectrum and a valuation on the residue. So also this description is quite concrete, right? You don't have to bear in mind that you are working with absolute values from an abstract algebra, and this somehow gives you a geometry space, but you can see it as a vibration over the spectrum, and this gives, in my opinion, a better understanding of what's going on. Anyway, so this extends, let me just repeat this here. So elements here are pairs. The valuation is here and the point is here. And what is interesting is that we can embed the space of rational points. Recall the rational points are here. Here, K is algebraically closed and characteristic 0. So I may wonder what is the fiber over rational points. And this is easy because if you take a rational point, closed point, a K rational point, a closed point, then K of X is equal to K itself. So what you are doing is that K embeds in K, and you are looking at valuations which go from the residue field to here, such that it commutes with the valuation that you already had. But this inclusion is just the trivial one, because it is the same field. So it's telling you to look at all the valuations such that this commutes, and it is not hard to see that the only valuation that does that is just the evaluation that you had before. So this means that there is a section here, right, which sends X. So the corresponding point here is just W is X with the valuation that you have in your field. So this tells you that state rigid spaces can be recovered from Berkovich spaces because the maximal ideals are recovered inside Berkovich and analytification as valuations which are defined by closed points. So this is why I made this drawing like this before, because what we are fully witnessing is that Berkovich is an enrichment of states, but not very exotic one, not very different, because the topology is still the same. It's defined by rational subsets, and the sheaf is defined in a slightly different manner, but still you get to embed the blue space in some big space, which is the green one. So this is not misleading, to be honest. So just to finish, the advantage, let me tell you some advantages of Berkovich theory over dates. Okay, so we have here a section of this projection, and we see that the fiber here is a point, right? Just fill this diagram up. I have here a copy, and the fiber is a point. Okay. So what are the advantages of Berkovich over date? So the first one, which really can be called an advantage, is that you can copy many geometric, or let me say many complex analytic constructions. In the Berkovich setting, because you have a topological space. So, for example, if you are happy working with line bundles, analytic or holomorphic line bundles in the complex case, you may try to define non-Archimedean analytic line bundles over QP, right? By somehow inspiring yourself from the complex case, right? I mean, here is I should include the topology. Or, for example, you can define line integration. You can define currents. You can define, I mean, if you have a concept from complex geometry, then you may try to use the same definition or some related definition to set up a definition in the Berkovich side. And this is not true for dates, because date is not a topological space. It is a site. So pretty much in dates approach, you are constrained to work with sheaves. And here you can do geometric things. Another big thing that I really like is that, just let me put it here, just to not lose more time. Another advantage is the theory of skeletons. Oh, I'm sorry, skeleton. Theory of skeleton is really something which you see in Berkovich, and you don't see skeleton dates geometry as far as I know. So theory of skeleton is, roughly speaking, so if you see this, so this was one of the first questions in which Berkovich was interested into, is what was like what is the topology of these guys? Right? So this is a question which makes sense in Berkovich and it does not make sense in dates, again, by the same reason. And he invented the theory of skeleton. This is a very general theory. I'm not going to say what it is, but it gives you a really good link with combinatorics. So this is a bridge, if you want. Here, there are these monsters, which are complex analytic spaces, which are absolutely massive. I mean, they have a structure which may fear us. So the theory of skeleta brings you from this world of analytic spaces to the world of combinatorics in a very precise way. And also this pretty much everything that I said here holds for other fields, not only the p-adics. Of course, you may consider other fields which are endowed with an absolute value, which is a non-Archimedean, for example, finite fields, or for example, formal power series fields over finite field. And you can pretty much do everything that I said here. You just have to worry about algebraic sublattice. For example, Skeleta, in a very precise way, they give you the homotopy type of these guys using some finite complex which you can build inside this Berkovich space. So, for example, in the famous example of Tate, if you have an elliptic curve over the p-adics, or let me be more geometric, take the field of Puiseux series. So you can show that the analytification of A is of two types. The first type is that you get, as I told you, you repeat pretty much the points which are closed, right, together with the generic point. You do the same thing here, together with the generic point. And two things may happen when you analytify an elliptic curve. The first thing is that you may find a special point, x, such that the residue field of x, the transcendence degree of the residue field over the base field, I'm thinking of this about k, I'm sorry, is 1. Either this x exists or it does not exist, right? And if it exists, then you can show that the analytification in the first case, you can show that this guy is homotopically equivalent to a point. And in the second case, if this guy does not exist, this means that the transcendence degree of any residue field of any point over your base field is 0, then this guy is homotopically equivalent to a circle. So there is a circle that sits inside here, and this result tells you that everything can be collapsed in an ordered way. That the topology, there is no more topology in this space other than the described by this blue circle. And in this case, in the first case, in the above case, it's telling you that there is no topology at all, because this space can be shrunk to a point. However, there is some sort of arithmetical information in the disguised as a special point whose residue field is an elliptic curve over the. I'm sorry. Here it should be the residue field of my base field. So anyways, this is something that you get from the theory of skeletons, sorry. And just let me tell you, so this is pretty much what I wanted to say about Berkovich spaces and the relationship with rigid spaces, which is concretely stated by image here. So you can see pretty much Berkovich as an enhancement of states. And now, also, I have been discussing here the relationships with the classical point of view of non-Archimedean analytic geometry, which is to come up with some nice theory of analytic functions over non-Archimedean fields. Let me just finish with this. The classical point of view is the nostalgic. The nostalgic in the sense that you have here a paradise, right, which is called the complex numbers. Everybody is happy. Everybody is nice because this is a perfect world, right? I mean, it's infinity. It is really beautiful. It is really nice. Everything works as expected. The classical or nostalgic point of view is that perhaps you have a more rocky background, right? So you also have here it is the beach, and maybe you go to a place in which the coast is not as smooth as in the complex case. So here is CP, and here is your sun. And perhaps you are not as happy as with the complex, but this does not prevent you of making a picnic here as you would do over here, right? This is the nostalgic in which you want to copy what you had previously on the complex case. And this was somehow pretty much the point of view that we had from 1940s to perhaps 2000 and something, perhaps 2011. So this starts with the work of Krasner. Then, of course, there is Tate, there is Berkovich, etc. But then from 2011, we got a beautiful manuscript by Fujiwara and Kato, which is in the bibliography, by the way. It is called Principles, something like this, right? Principle, let me just give you the greatest answer. So it is called the Foundations of Rigid Geometry. It is this little guy. So it is now published by the European Mathematical Society, and the big change of point of view is that we are no longer longing for what we have, but we accept our reality and we try to be happy with it. So this is a big change in the motivation and the point of view of rigid geometry, because any time that you compare with some perfect situation, you are not going to be happy because your endeavors are not going to be good as you want. You will be always comparing to the ideal, but you won't get it by transcendental reasons, right? And the change of point of view is that, okay, you were born here, this is what you have, and try to be happy with this. And maybe you can do beautiful things, maybe different things, which are not, which cannot be compared with what our previous generations of mathematicians had done, but there is no problem. Try to do some new things without considering that this exists. So let's start anew, fresh start, and just forget about this. And I'm going to finish with this. Fujiwara Kato tells you, okay, let's try to, to understand rigid geometry, but not in the sense of tape. And this is something that may be maybe a mistake by them, because when you read here rigid geometry, you may wonder, okay, this is Tate's business. So I have several bibliography about this. So why should I pick this book? But this is not rigid geometry as Tate intended to construct. This is a new kind of rigid geometry, a broader kind, in which they use some sort of Zariski-Riemann spaces and some formal birational geometry to set up a better, in my opinion, well, let's not call it better, a different setting for rigid geometry, which swallows Tate, also Berkovich. I'm sorry I didn't have much time to discuss about Huber, right? But all these guys, or also Reynaud, all these approaches of rigid geometry that we have previously considered, not perhaps not here, but they are not long. They are not quite distant from what we said here, can be seen as special incarnations of this theory. And I really encourage you to check out this book. It is available as a preprint in the archive if you want to learn more about this kind of technology. Okay, I think this is all I have to say. Thank you very much.